Welcome to AI Frontiers, where we explore cutting-edge research reshaping our technological future. Today we're examining a computer vision renaissance happening right now in laboratories worldwide. Picture a machine that watches someone walking down a street and doesn't just see moving pixels, but actually understands the three-dimensional world, predicts where that person will go next, and can even imagine how the scene would look from a completely different angle. This isn't science fiction anymore. It's the revolutionary reality of visual AI in 2025. When machines truly see, they move beyond simple pixel processing to genuine understanding. Imagine the difference between a basic camera that merely captures light and an artist's eye that comprehends emotional content, predicts future actions, and reimagines scenes in entirely new ways. Modern AI systems are achieving exactly this transformation. A machine can now watch a video of someone walking and not only track their movement, but predict their destination, understand the spatial relationships in the environment, and even generate views from angles never captured by the original camera. This represents a fundamental shift from passive observation to active visual intelligence. Computer vision represents one of artificial intelligence's most ambitious goals, teaching machines to see and understand the visual world with human-like sophistication, and often surpassing human capabilities entirely. The field encompasses everything from basic image recognition, distinguishing cats from dogs, to complex scene understanding that analyzes relationships between multiple objects, people, and environments in real time. What makes today's research particularly exciting is how it pushes beyond traditional boundaries. Modern computer vision systems serve as active participants that generate new visual content, manipulate existing images with unprecedented precision, and simulate entire worlds. This technology powers autonomous vehicles navigating busy intersections, helps radiologists detect cancer with superhuman accuracy, and enables augmented reality experiences in daily life. The interdisciplinary foundation draws from mathematics, neuroscience, physics, and cognitive science, creating increasingly sophisticated algorithms that rival and sometimes exceed human performance on specific visual tasks. Deploying powerful computer vision models in real-world environments presents what researchers call the Formula One challenge. It's like trying to run a Formula One race car on city streets. The most sophisticated AI models require massive computational resources, but practical applications need these capabilities on smartphones, drones, and embedded systems with limited processing power. This challenge isn't just about making systems faster, it's about democratizing access to advanced AI capabilities. The goal is making sophisticated visual intelligence available to everyone, not just those with access to supercomputing resources. This requires fundamental breakthroughs in efficiency without sacrificing the performance that makes these systems valuable. The first major theme driving computer vision forward is the efficiency revolution, exemplified by the SemanticVLA framework breakthrough. This innovative approach introduces semantic-aligned sparsification techniques that make robotic manipulation systems 3 times more efficient while simultaneously improving performance by 21%. The framework addresses the critical challenge of deploying sophisticated AI in resource-constrained environments. By optimizing how models process and store information, SemanticVLA demonstrates that efficiency gains don't require performance trade-offs. Instead, smarter optimization can achieve both goals simultaneously. This breakthrough makes advanced robotic capabilities accessible for deployment on mobile platforms, edge devices, and systems operating with limited computational budgets, fundamentally democratizing access to state-of-the-art visual AI capabilities. The second transformative theme involves three-dimensional understanding breakthroughs, with Depth Anything 3 leading a spatial revolution in computer vision. Researchers led by Lin and colleagues achieved 44% better camera pose accuracy compared to previous state-of-the-art methods, using surprisingly simple architectures that challenge conventional wisdom about complex system design. This advancement represents the difference between looking at a photograph of a room and actually understanding the room's layout, depth, and spatial relationships between objects. The implications extend far beyond academic research, enabling robots to navigate three-dimensional environments more effectively, autonomous vehicles to better understand their surroundings, and mobile devices to create accurate spatial maps from limited sensor data. The discovery that plain architectures can outperform specialized three-dimensional systems suggests that better training methodologies may be more important than architectural complexity. The third theme focuses on multimodal detective work, where AI systems combine vision, text, and audio intelligence, like detectives, analyzing multiple types of evidence to solve complex cases. Frequency-aware vision-language networks demonstrate how combining visual and textual information can dramatically improve performance across different domains and conditions. These systems don't just process images or text separately, they understand the relationships and complementary information across modalities. A multimodal AI system analyzing a crime scene phonograph can simultaneously read witness statements, analyze audio recordings, and combine all this information for deeper understanding than any single modality approach could achieve. This integration enables more robust and reliable AI systems that can handle the complexity and ambiguity of real-world scenarios where information comes from multiple sources and formats. Revolutionary discoveries are reshaping the field through 5 key findings that seemed impossible just years ago. First, plain transformer architectures now outperform specialized three-dimensional systems, challenging fundamental assumptions about complex problem-solving approaches. Second, data attribution for text-to-image models has become 2,500 to 400,000 times faster while maintaining accuracy, enabling real-time analysis of AI-generated content sources. Third, medical imaging advances show 11 to 54% improvements in localization accuracy with parameter-free three-dimensional architectures. Fourth, self-consistency sampling approaches demonstrate up to 7.7 percentage point improvements across multiple benchmarks with minimal additional computational cost. Finally, graph-based approaches achieve comparable performance to existing methods while using significantly fewer trainable parameters, making advanced three-dimensional understanding accessible in resource-constrained environments. Today's featured research, Depth Anything 3, by Lin and colleagues, represents a fundamental shift in three-dimensional visual understanding that challenges everything researchers thought they knew about architectural design. This work tackles one of computer vision's most challenging problems, recovering consistent three-dimensional structure from multiple two-dimensional images when camera positions are unknown or uncertain. The system achieves 44.3% better camera pose accuracy and 25.1% better geometric accuracy compared to previous methods. However, the real breakthrough lies in discovering that a single plane transformer encoder outperforms specialized systems carefully designed for three-dimensional tasks. This finding challenges the fundamental assumption that more complex problems require more complex solutions, demonstrating that better training methodologies and problem formulation can be more important than architectural complexity. The human story behind this innovation reveals months spent questioning the complexity arms race in computer vision architecture design. The research team persistently explored counterintuitive solutions, repeatedly asking whether increasingly complex architectures were truly necessary for three-dimensional understanding. The moment researchers realized a plane transformer was outperforming specialized architectures was described as both shocking and liberating, opening entirely new research directions. This discovery emerged from questioning conventional wisdom and exploring simpler approaches when the field was moving toward ever more complex solutions. The breakthrough demonstrates that better training paradigms, including teacher-student approaches where complex models guide simpler ones, can achieve superior performance while maintaining computational efficiency. This persistence in exploring elegant simplicity over architectural complexity has fundamentally changed how researchers approach three-dimensional visual understanding problems. The transformative real-world impact of these advances extends across numerous applications that will reshape daily technology interactions. Smartphones will soon create accurate three-dimensional models from just a few photographs, enabling augmented reality applications that seamlessly integrate digital content with physical environments. autonomous vehicles will better understand their surroundings using limited sensor data, improving safety and navigation capabilities in complex urban environments. Professional-grade three-dimensional reconstruction will become accessible to anyone with a camera, democratizing capabilities previously reserved for specialized equipment and expertise. The simplicity of these approaches makes them more likely to be widely adopted, as simpler models are easier to implement, debug, and maintain in real-world systems. Additionally, this research establishes new benchmarks and evaluation protocols that will accelerate future progress by providing standardized ways to measure advances in visual geometry tasks. Looking toward the future, these advances point toward a world where the boundary between digital and physical reality becomes increasingly fluid. AI systems will understand three-dimensional scenes as intuitively as humans do, but with the precision and consistency that only machines can provide. Creative tools will generate entirely new visual styles on demand, enabling artistic expression in ways never before possible. Medical systems will detect diseases in their earliest stages with unprecedented accuracy, potentially saving countless lives through earlier intervention. The convergence of efficiency improvements, three-dimensional understanding, and multimodal integration suggests we're approaching a tipping point, where sophisticated visual AI becomes ubiquitous. These systems won't just be tools we use, they'll become intelligent partners that can see, understand, and reason about the visual world alongside us, augmenting human capabilities in ways we're only beginning to imagine. These advances represent more than technical progress. They provide a glimpse into a future where machines don't just process visual information, but truly understand it with human-like sophistication and beyond human capabilities. AI systems will create, analyze, and reason about visual content in ways that seemed impossible just years ago. From the elegant simplicity of Depth, Anything 3's architectural breakthrough, to the creative possibilities of style-controlled image generation, these advances lay the foundation for applications we can barely imagine today. The research demonstrates that the most profound breakthroughs often come from questioning fundamental assumptions and exploring counterintuitive approaches. As these technologies mature and converge, they will enable new forms of human-machine collaboration, where artificial intelligence augments and extends human visual understanding, rather than simply replacing it. The future of visual AI is being written right now, and these 17 papers represent some of its most important chapters. This analysis was synthesized using Claude Sonnet 4, released May 14, 2025. With text-to-speech synthesis provided by DeepGram technology and image generation through OpenAI systems. The content underwent human expert review to ensure accuracy and clarity in presenting these complex research findings. While every effort has been made to accurately represent the original research, possible oversights may remain, and listeners are encouraged to consult the original papers for complete technical details. All references and links to the original research papers are provided in the show notes, along with information about publicly available code and datasets. This synthesis represents our commitment to making cutting-edge AI research accessible to broader audiences, while maintaining scientific rigor and accuracy in our presentations. Thank you for joining us on AI Frontiers as we explored these groundbreaking advances in computer vision research. We encourage you to explore these papers yourself using the links provided in our show notes, and many researchers have made their code and datasets publicly available for further investigation. Share your thoughts about these breakthroughs on social media using the hashtag AI Frontiers, and let us know which applications excite you most about the future of visual artificial intelligence. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv preprintserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv preprintserver.org.